heterogeneous AI or memory module can pass an isolated electrical review and still fail once stack-up, assembly tolerances, power delivery, hotspots, cooling, and test access begin interacting. That is why choosing a D-SiP supplier cannot be reduced to package density, equipment lists, or labels such as 2, 5D, 3D, chiplet, and system in package. The real buying decision is whether the supplier can demonstrate project-specific ownership from architecture through controlled production. The procurement object must be defined first. Responsibility may include package architecture, substrate or interposer selection, simulation assumptions, floor planning, design for manufacturing review, test planning, pilot build analysis, and failure escalation. OEMs should establish who owns each activity and how decisions connect to formal review gates. Heterogeneous integration creates failures that may not belong cleanly to one die or one process step, making system-level accountability essential. Every candidate should receive the same technical brief. It should identify die categories, known good die status, interfaces, bandwidth targets, power ranges, environmental conditions, dimensional limits, cooling assumptions, test requirements, anticipated volume, quality documentation, and change control expectations. A quotation issued without these constraints may indicate commercial interest, but it cannot establish feasibility. Supplier evaluation should then cover 5 evidence domains. The first is design and integration. Request the required design inputs, interface assumptions, floor planning logic, power and ground strategy, substrate or interposer considerations, and the limits that would force an architectural change. The objective is to see how the supplier resolves conflicts among die compatibility, package size, electrical performance, thermal behavior, and test access. The second domain is electrical and thermal validation. Simulation results only become meaningful when their assumptions are visible. Suppliers should identify boundary conditions, material assumptions, provisional inputs, interface constraints, signal and power integrity scope, thermal hotspots, and the method for correlating models with prototype measurements. A favorable result without operating conditions, tolerances, and a correlation plan is not release-ready evidence. Manufacturing and test form the third domain. The package must move from an engineering file into a repeatable assembly, inspection, and test process. Evidence should address design for manufacturability review, process windows, die handling, inspection points, test access, traceability, pilot reporting, and criteria for a controlled ramp. The fourth domain is reliability and failure accountability. Buyers need a product-specific plan connecting applicable stresses, pass criteria, sampling, escalation, failure analysis, corrective action, record retention, and disposition authority. A list of available test names does not define what happens when qualification samples or field returns behave unexpectedly. The fifth domain is engineering collaboration. Advanced package decisions change quickly as die availability, test coverage, design revisions, and production conditions evolve. Review the supplier's milestones, response cadence, document control, change notification rules, prototype feedback format, and handoffs among design, operations, and quality. These controls preserve the value of technical evidence throughout the program. For release gates, turn that evidence into decisions. Gate 1 aligns architecture and constraints, recording unresolved information as assumptions. Gate 2 reviews electrical, thermal, mechanical, and manufacturing feasibility together, including sensitivities to stack-up, placement, geometry, tolerances, and cooling. Each residual risk needs an owner, a correlation method, and a scheduled review point. Gate 3 compares prototype and pilot build measurements with design assumptions. Electrical results, thermal behavior, inspection findings, assembly observations, test coverage, and early yield signals should be assessed together. Deviations require documented engineering review, not informal adjustment. Gate 4 establishes controlled release. Specifications, acceptance criteria, process controls, traceability, and change management rules must be ready for the intended production stage. Material changes, approval authority, and downstream investigation paths must be clearly defined. Supplier pages and rapid RFQ responses can identify prospective fit, but they are starting evidence, not final proof. A defensible decision comes from common inputs, comparable documentation, cross-functional review, explicit risk ownership, and disciplined progression through all 4 gates.